Hello, this video is entitled Sequences. Now, many of you have possibly studied sequences in a pre-calculus type course or whatever, but there will be a calculus aspect to this also because we will be evaluating limits. So you might should see some things you haven't seen before. I write a sequence. List of terms, each value is a term, kind of a pattern here. So this is 2, 4, 6, 8, 10, so forth, so on. Each value is a term of the sequence, and then AN actually represents the formula that generates each term, if there is one. Now, assuming we were to start with A1, it could be possible to start with something else, but 1's the general starting point here. So you would call the first term A sub 1, second term A sub 2, A sub 3, so forth, so on. So the pattern for this sequence would just be 2 times n. So meaning if you wanted to find the 30th term of this particular sequence, you would not have to keep going 10, 12, 14, 16, 18 forever. You would just put 30 in here and say that 2 times 30 is 60, and you'd have it. Now, listing terms on a sequence based on a formula, that's pretty easy. This is telling us to list the first 5 terms of this sequence. A sub n equals negative 2/3 to the n. So you see, all I do is just change the exponent. 1, 2, 3, 4, 5. So it's negative 2/3 to the first, to the second, to the third, to the fourth, to the fifth, and it will generate these 5 terms right here. Okay, that's easy enough. Now let's talk about a recursively defined sequence. That's a little bit trickier. There's actually one very, very famous recursive sequence. Recursive means that you're using previous terms of a sequence to determine the next term. In other words, you can't just plug, some n directly into a formula. You have to use a previous result. So, like for example, to get the 10th term, you might need the 9th term and possibly more terms than that to get to that term. So this Fibonacci sequence is starts out, some people argue starts out with 0 and 1, but it really doesn't matter if that 0 is there or not. Well, let's just say it starts out with 1 and 1. It's giving you the first 2 terms. And then here's the formula for it. Where a sub n starting at 3 equals a sub n minus 1, which will be a sub 2, plus a sub n minus 2, which will be a sub 1. That's just a fancy way of saying it's adding the previous 2 terms together. So if you start with 1 and 1, the next term would be 1 plus 1 is 2. Then you have 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, and so forth and so on. It would just keep going on and on and on, that pattern. Now, I don't want to diverge too much here from the discussion, but because you can certainly look at this on your own. But the Fibonacci sequence and some of its nature applications, and this is called the Fibonacci spiral that's graphed based on those numbers. Now, it's hard to see right in here. There's a 1 and a 1, so you put a 2 square next to it, and you're kind of going corner to corner. It's going 1 up to that corner, then down to that corner, and then you put a 3 right below that because that's the next term, and then hits that corner, and then 5 is the next term. 2 plus 3 is 5, so a 5 square fits right here, and then it goes in like this, and because you have a 5 and a 3, you got a width of 8 here. So it hits that corner, 8 and 5 make 13, hits that corner, and just keeps spiraling like that. That's where the visual aspects come into play. Well, other areas too, even without the spiral, certain types of trees will grow a number of branches based on the Fibonacci sequence. But there's shells, here's the trees coming up. There's shells look like that, trees, there's no picture of any of the ones, but Flower pistils, petals, leaves will often branch out into a Fibonacci sequence. And I got like the storms. They mentioned galaxies, because I've heard that certain, like, look at galaxies into a spiral type of. Oh, then the human face. Look at the ear right there. Various patterns of Fibonacci spirals for different parts of the face. All right, so we don't need to worry about that. But I thought that was at least something worth showing, because like I said, it's a pretty famous sequence. Now, let's see if we can list some terms out of a recursive sequence. Now, this is a little more challenging than just plugging them into a regular sequence formula, like I did with that last example with 2/3 to the n. But once you kind of get the hang of it, it's not too bad. Now, this particular book I'm working with is using k instead of n, but that's the same thing, k and n. So you've got to be started with some value of this thing. You can't, if you have something where it's just, for example, let's say if a sub n is defined as 3n plus 2, well, then you can put in any n and figure out what that term would be. But since these are recursive, they're using prior terms, you got to have something to start with. So for this one, they're telling us a sub 1 equals 6. And then a sub k plus 1 equals 1/3 times a squared of k. And then want the first 5 terms. Now with the recursive sequences, you're given at least 1 or more terms. You're not going to have to figure out 5. So this one, we're already starting. We know 6 will be the first term. And then the next one we calculate will be a squared. A sub 2, excuse me. So to get a2, you're putting 1 in there for k right here. So a sub 2, the second term, will be 1/3 times a sub 1 squared. So a sub 1 squared is 6. So it's 1/3 times 6 squared. 1/3 times 36 is 12. So what you're basically doing in this pattern for this sequence, this recursive sequence, is the next term will be 1/3 times the square of the previous term. And that's all you got to do. So once you kind of see how that pattern develops, it's real easy from there. So a3, to get a3, we have to use this result from a2. So you see this 12 is going to go right into here. And a3 is 1/3 times 12 squared, which is 48. And then a4 is going to use a3. So it'll be 1/3 times 48 squared. And that'll be 768. And the last term, then a5 that we want, will be 1/3 times the a4, 768 squared, which is 196,608. And there we go. That's recursive sequence. Let's talk about factorials here. These will come up, we'll use them now, and then they'll come back up again a few sections later. Factorials are used in what's called combinatorics, just a fancy way of saying counting, ways to count things, often use factorials. For example, if you want to know how many ways can 6 people sit in 6 chairs, that would be this kind of idea right here. Or how many different orders could you hang like 5 paintings in a row, across a row on a wall? What would be the different number of ways you could hang them? That's where this kind of comes in, this factorial. Now the idea of a factorial, it's n, or your calculator may have x. It doesn't matter that it's commonly used as n, but if your calculator says x factorial, that's all right. Exclamation mark. Some people call it the angry n. It's like it's shouting at you. Like, n. It means its value of n times n minus 1 times n minus 2. So you get all the way down to 1. And with 2 restrictions here, that 0 factorial is actually 1, meaning there's kind of one way to have nothing. And then 1 factorial is also 1. So you wouldn't go 1 times 0. You would just stop right there and call it 1. But 0 factorial kind of has to be 1. If we were getting more into this, you'd see why, but we're not. Now we're going to be doing these algebraically, but these are real easy to do in the calculator. They have a factorial key there. You have to put the value, the number first, and then you go math PRB, and you go down, and then you're looking for the exclamation mark. Some scientific calculators have the factorial key on the keyboard, like a second function or something, but the TIs have it kind of hidden in there. So for example, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which would equal 40,320. Yeah, these factorial numbers could get pretty large in a hurry. Because it seems kind of mind-boggling that if you took 8 people in 8 chairs and how many different orders they could sit, there's 40,320 ways they could do that. That just seems really large, I know. But now here's an idea. Sometimes calculators can only handle so much large numbers for factorials, and we're going to need this for our algebraic methods here in a minute. But just kind of show you how this works. If you were simplifying factorials, if you take the largest one of the two, anytime you're counting it down here, like in this case you go 199, because the important thing is we're starting with the larger one, times 98, times 97. Anywhere that you want to stop that pattern, you can put an exclamation part for the factorial, exclamation mark, and that automatically then carries it down to 1. Well, for this particular example, I naturally would want to stop it with the 97 factorial that I have on bottom. So I stopped right here, allowed these two to cancel. So 100 factorial divided by 97 factorial is the same thing as 100 times 99 times 98, which is this number right here. So that's going to be very important for what we're about to do here. Simplifying factorials algebraically. So we have n plus 2 factorial divided by n factorial. So what you're doing is you're looking for the larger of the two factorials. The larger may be on top, or it may be on the bottom, which we'll see in the next example, whichever is larger. Well, n plus 2 is larger than n. So what I want to do is start counting it down from here by subtracting 1. I go n plus 2 times n plus 1, subtract 1, I have n. Now I want to stop here because I'm looking to stop with whatever matches the denominator. So if I go n plus 1, I go n, I can put a factorial there, and then that matches the n factorial on the bottom. They would cancel. So that means n plus 2 factorial divided by n factorial would always equal n plus 2 times n plus 1. Let's look at the next one. N minus 3, n minus 3, and divided by n factorial. N factorial is larger than n minus 3 because you're subtracting 3, not plus 3. Obviously, n plus 3 would be greater, but n is greater than n minus 3, so I start with that one. I start with n, I subtract 1, n times n minus 1 times n minus 2, subtract 1 more is n minus 3. I stop there because that matches the top, and then I write it as a factorial, and I cancel the factorials. So that would simplify as 1, and then divided by n times n minus 1 times n minus 2, all on the bottom. Now let's talk about the limit of a sequence. Okay. Now when we say find the limit of a sequence, it automatically means, because we'll be using n, it automatically means that n goes to infinity. You know, which in regular limits, even go back to L'Hopital's rule or even earlier on in Cal 1 and things like that, you know, you find the limit of an algebraic expression, you have to know what x is approaching. It has to tell you. But here, for sequences, it's just implied that it's infinity. So if it says find the limit of a sequence, that automatically means every time n is going to infinity. So that's why that information could be left out of a problem. Yeah, like unlike an algebraic one, if I said, well, find the limit of the natural log of x divided by x, and just said find the limit. Well, that doesn't accomplish anything because it has to tell you what x approaches. But not here. We don't have to worry about this algebraic part here. But basically, we're going to find the limit of the sequence, sort of like we would an algebraic way. And if the limit exists, the value L will be the result of that limit. Otherwise, we'll say, DNE for does not exist if it doesn't. So it's just kind of evaluating limits the normal way. We're just kind of using n's here because we're replacing f of x with a to the n. So it's a function of n now. So it either converges to some value L or it just flat out diverges. We don't have to worry about, answering. Diverges is pretty much going to mean infinity, but just the answer diverges is sufficient. So, when it converges to a real number. So you would never say converges to infinity or like diverges to 3 or something like that. So obviously those are contradictory expressions. So let's take a look at these limits. Now this is 2, 4, 6, 8, 10. The formula is 2n. The limit as n goes to infinity, so the limit of this clearly goes to infinity. So it diverges, and you can kind of sort of see that because if the terms are steadily increasing like they are here, well then it's not going to have a limit. It's just going to go on and on and on forever. Now the next one, 1/3, 1/5, 1/7, 1/9, 1/11. You could probably do this without the formula, but I would give you the formula for this. It's 1 over 2n plus 1. We'll take a look for a little bit of how to figure out these formulas, but I generally don't ask it on an exam. Certainly not a multiple choice exam because it would be too easy just to plug the numbers in and see which one was the right formula. Handwritten test, maybe. But anyway, 1 over 2n plus 1 as n goes to infinity. That's clearly 1 over infinity, so that's going to converge to 0. So in other words, that fraction's never going to be 0, but obviously the idea of limits, you never have to reach that amount, do you? It just has to approach it. So we'd say is it, goes to 0. So that converges to 0. Let's look at this one. Find the limit of this sequence. an equals 3n plus 2 over 5n minus 3. So there we go. Now, yeah, you could use L'Hopital's rule here, but you can kind of use some basic methods from Cal 1 also to do it. Because, we're not looking for, the formal process on this or anything. So, but you look at this as, since it's only because this is infinity, which these will always be infinity, is that you have largest exponent top and bottom are the same power. So that means the limit will be the ratio of the coefficients. So it would be 3/5. Okie dokie, let's see. Here's some properties of limits. They're pretty straightforward. I probably won't just read all these out. I'll let you look at them yourself. But, just like one thing about limits that we already have learned, but unlike derivatives, the limit of a product is the product of the limits. Same thing with quotients. But not true for derivatives, obviously. That's why we have product rule and quotient rule. So I'll leave those up there. I won't read those, but I wouldn't worry too much about those. Kind of just common sense, if you have like two or more terms added or subtracted, it just means you can evaluate the limits individually. All right, here's the instructions. Find the limit of the sequence. So as I mentioned earlier, that's all the instructions we need because that means automatically we are going to infinity. All right. So 8 plus 5 over n, so the limit is 8 plus 5 over n. You can split these up individually. So we have the limit of 8 as n goes to infinity. Then we have the limit of 5 over n as n goes to infinity. Now, the limit of a constant, going back to Cal 1, is always a constant, no matter what this is approaching. So that's 8. But then 5 over n will go to 0 as n goes to infinity. 8 plus 0, so you would say converges to 8. Now here's another one that kind of uses the idea I used on the last page, is that you have the same exponent, n to the 1/3, n to the 1/3. Now I just wrote these ones here to show you that, I am looking at their coefficients. So you got a 1 divided by 1 makes that converges to 1. I guess I forgot to put converges 2 in there. I guess I could fix that real quick. And now it's prepared to say converges to 1 here. Let's look at the next one. Sometimes you have to use a little creativity here. This one, it's hard to really apply normal limit rules. This one, you kind of list out the terms of the sequence, and you can sort of see what's going on. Now, if I put 1 in here, starting with a sub 1, negative 1 to the 1 would be negative 1. 1 plus negative 1 is 0. If I put 2 in here, negative 1 squared is 1. 1 plus 1 is 2. If I put 3 in here, negative 1 to the 3 is negative 1, plus 1 is 0. Now we've got a pattern. Every time that we're on an odd term, it's going to be 0. And when we're on an even term, it's going to be 2. So what's happening here is that this sequence is just toggling back and forth from 0 to 2, meaning it's never converging on one of those two values. It's just alternating between them. It's never approaching anything. So that would be enough to say diverges. So here's an example, I might have mentioned earlier, diverges, usually is infinity. But here's an example of where a sequence can diverge, and infinity was not the reason for it. Yeah, I put this in Maple. Maple kind of gave this weird answer, 0, dot, dot, 2, so I don't know. Maybe the dot, dot means the alternating terms, but point is, it did not give a normal answer. That's not 0.2, because there's 2 dots in there. How about this next one? Cosine of 2 over n, as n goes to infinity. So you look at this, you look at it like this. I wrote it right there, but you don't have to obviously write that out if you don't want to. You can just kind of eyeball it like I'm about to explain here, and go, all right, well, infinity, 2 over n, 2 over infinity will go to 0. Therefore, cosine of 0 will go to 1. And there we have it. So it converges to 1. Maple likes that answer. Now here's something I copied from my Cal 1 notes, and actually this goes back to even, well, Cal 1 notes. I was going to say, without using the word limit, I used to use this method for finding horizontal asymptotes in college algebra. It's a good method, but obviously when you put limit in front of it, it's a calculus concept. So so I've already done this a couple of times with a couple of examples before I put this rule in here, but so I think you can kind of figure this out. So if they're equal exponents, which we've had twice now, m equals n. And this might have come up in L'Hopital's rule also, section. So it would converge the coefficients a over b. If m is less than n, larger power on bottom, it's going to go to 0. Larger power on top, it diverges. Let's take a look at this. So you see this one has a n squared on top, n cubed on bottom is going to go to 0. n5 on top, n4 on bottom goes to infinity. One thing I want to mention is don't always assume that the larger terms are written first. They were in this case, but you never know if they'll reverse the order or something. So you just kind of want to look around carefully. But for this one, you have 10n squared over 2n squared. So it's just 10 over 2. So it converges to 5. Now this next one's kind of interesting, because that numerator, clean this up while I'm talking about that. That numerator is a problem that we just did recently. The one that alternated between the zeros and the 2's. And so it's probably tempting to think, okay, well, fella, that's not going to, I've already seen this movie, so, I know it's diverging. But the dividing by n squared does make a difference here. Because, yes, you're alternating between 0 and 2 on top, but you have a growing denominator. So you got 0, 2, 0, 2, yeah, all day long. But because the denominator is going towards infinity, so whether it's 0 over infinity or 2 over infinity, it's still going to go to 0. Now, I'm not going to, test you directly here on this thing called the Squeeze Theorem from Cal 1. It's all right, but I just tried to show you. The Squeeze Theorem says if you can absolutely place your limit between two other functions, and if those two outside functions have the same limit, then the other one, because it's squeezed between those two, would have to be the same limit. So we know that the numerator is going to be either 0 or 2, right? So I put it between -1 and 3, and they're all over n squared. Well, the limit as n goes to infinity of -1 over n squared will clearly be 0. 3 over n squared will clearly be 0. So that means the middle one would have to be 0 then for that reason. So if you like that better than me just saying it's going to be 0, you've got a little more mathematical reason. And Maple liked it. So that's always good. I like it when Maple gets the same answer. So there we go. All right. Now we might need our friend L'Hopital's rule every once in a while here too. So now this one, because this is an indeterminate form, it's infinity over infinity. Well, technically some of these other ones are indeterminate forms also, but let me scroll back up here. I guess I'll clarify. Yeah, these are all indeterminate forms, but they were fitting, this rule right here, except for that weird last one we did. So if they're fitting this rule, this is a different scenario. If they don't fit this rule, then they probably need L'Hopital's rule. Those other ones could have been done. Well, actually, the one with the cube root of n would not have worked with L'Hopital's rule because it was a fractional exponent. The exponent never would have gone away. So it's just that this is using. So yeah, these are indeterminate forms that actually need L'Hopital's rule. So all I did here was use property of logs, make that n to the 1/2, bring the 1/2 down. And this is my notation that's not mandatory mathematically, especially if you're someone that's not one of my students taking my class, watching this. I use this star to indicate that I'm applying L'Hopital's rule, but that's not a mathematical rule. I could have just wrote this limit without that star because I'm just taking the derivative of the top. I pulled the 1/2 out, by the way. The derivative of the top of ln of n is 1 over n. The derivative of n is 1. So I now have basically just 1 over n. That's going to go to 0, so the 1/2 has no effect. So this will converge to 0. And for some reason, I made a table of values in the calculator, and was just showing that it was getting smaller and smaller and smaller. Now, factorials. Take a look at factorials. Now, here's an interesting, thing with factorials limits is that there's only one of two possible answers you can get for a factorial sequence limit two answers only. It's either going to converge to 0 or it's going to diverge. Because what's going to happen is either the n's are all going to be left on the bottom, like this example. So let me go through this one. Practice this. So n minus 2 factorial, n factorial. Start with the largest, which is n, on bottom. So I go n minus 1, n minus 2, cancel the factorials, and the n's are left on bottom. So when the n's are left on bottom, you automatically have converged to 0. This one, larger factorial on top. So you start there, n plus 3, n plus 2, then you have n plus 1 factorial. Cancels with that n plus 1 factorial. Now since the n's are all on top, it's going to go to infinity. So you're going to have diverge. So actually, there's a quicker way to do this without even without even simplifying the factorials. Is if you look at the problem and the larger factorials on the bottom, it's converging to 0. If it's on the top, it's diverging. You don't even really have to even work it out. So larger one on bottom here meant for sure converge to 0. Larger one on top here meant diverges. And sometimes in a multiple choice answer, I'll slip in something weird like diverges to 0. Well, that's like I was talking about earlier in the video. That's obviously a nonsense answer because diverging can't go to a real number of values. So now here's another sort of famous L'Hopital's rule thing we've had before. This is infinity times 0 when you put infinity in here. And don't assume going to infinity times going to 0 is going to equal 0. It does a lot of the times. This will be an example of where it doesn't. So you have to drop one of these two down to the denominator. It's tricky with these because there are some problems where you would drop the trig function. It's not like we learned in L'Hopital's rule when you have natural log, that must stay on top. Don't ever drop natural log. But this one, it makes more sense to put the n on bottom and you're making it 1 over n because that way when it flips over it becomes n. So you actually want to do it this way and it works out really easy. Because the derivative of sine of 1 over n with respect to n using the chain rule will be cosine of 1 over n times the derivative of 1 over n, which I left this way on purpose. Because if this is a derivative of 1 over n here, the bottom is also the derivative of 1 over n. So without even taking these derivatives, you can cancel them out. But if you do take the derivatives and you don't catch that, you can still cancel them out. They would both be negative 1 over n squared if you actually took the derivative, but that's just a little bit of a step saver, I think. So, and so what are you left with? You put infinity in here. 1 over infinity is 0. Cosine of 0 would be 1, so it converges to 1. Hey, Maple likes that answer. This one is not L'Hopital's rule, but the interesting thing about this problem is don't put the negative 3 in parentheses. Yeah, only if it was in parentheses. The negative 3 is outside of this. When you put infinity in here, 1 over infinity is 0. 3 to the 0 is 1, but the negative's still there. So it's actually converging to negative 1. So I can see how somebody might mess this up and they think it's all of negative 3 converted to 0. Yeah, I just wrote that out there to show you. So yeah, if it was negative 3 to the 0 like this, but it's not, but if it was this, then yes, the answer would be positive 1. But that is not correct. All right. And now we have cosine of pi n over n squared. Now this is another one that sort of has a kind of a squeeze theorem application here. But if you look at the cosine of pi n, and n's an integer, so you're starting at 1 pi, 2 pi, 3 pi. This is very similar to very similar to this problem we did up here. Let me scroll back up here. That. It's real similar to this. Guess I could copy this, couldn't I? Except this time, instead of going 0, 2, 0, 2, 0, 2, you're going negative 1, negative 1, no, excuse me, negative 1, positive 1, negative 1, positive 1, like that. But anyway, it's over n squared, so it's still going to be going to 0. So it was very similar to that other example. Moving this around a little bit, so yeah, so it's just going to go 0. Now let's look at this next one. Don't know why I have that written so far up the page there, but oh well. That's just cosmetic. Guess I did need the space there, didn't I? Yeah, unless I would have gone horizontally, it might have fit, but maybe I can try that real quick. Okay, so I've kind of cleaned this one up a little bit. Now, frankly, to be honest with you, we had this on the L'Hopital's rule section and would have had that on this test, but I don't really see this coming up on this particular exam, so I wouldn't worry too much about it. But this was the technique where you had the exponent. So this one evaluated to 1 to the infinity. I'm not going to spend a lot of time on this one because, frankly, I'm not going to put this on your exam 3. But I want you to make sure you get a good look at it here. But I'll just real quickly go through this. So it evaluates to 1 to the infinity. This is where you have to natural log both sides, and that'll bring the n down. And we don't drop the ln, so it's 1 over n. And some of these you just kind of have to sort of figure it out. Well, we have to do L'Hopital's rule first, and so then see what happens. So ln is going to be the derivative of this, over the derivative of the bottom. Got a negative to cancel here. And then you just kind of have to combine the terms. I drop this one down to the bottom, like so. And there could be more than one way to do this. But I distributed this through the parentheses, like so. And then to get rid of all those fractions, I just multiply top and bottom by n to the 4th, because that was the largest power for n, and that kind of got rid of all the fractions. And then it turned into this 2n over n squared plus 1, and then we're home free. Of course, that limit equals 0. However, the answer is not 0. Remember, in these kind of problems, you have to then rewrite it as, that means the natural log of that limit equals 0. So we just have to take e raised to whatever that answer was. And so ln of y equals 0, e to the 0, so we converge to 1. And Maple says it. Maple has it in there as 1, so I like that. Formulas for sequences. I was going to go through this real quick. I don't really plan on asking this either. Certainly not if you're taking an online class. Maybe face-to-face, but I would make that real clear in class. I would probably just go over this too more carefully. But all right. So you see this one 3, 7, 11, 15 is increasing by 4. So it might make you think the formula is going to be something plus 4, which seems logical. Sometimes there can be more than one correct formula for these two. But actually, the common difference is what, which is 4 between each term, is the multiple for this n. So we have, it's going to be 4n. Then what you do, so it's going to be 4n, then you're going to put this constant here, and then you're going to put the constant in there based on what would make it fit. In other words, if I put 1 in there, a1, I have 4 times 1, which of course is 4. What would I need to do to make it match my first term? Well, I would need to subtract 1 because I want it to be 3. And then that way when you put in 2, 4 times 2 minus 1 is 7. And there you go, 4n minus 1. The next one with these fractions, because the numerator and the denominator are both increasing by the same, we're increasing by 3 on the numerator, so it'll be 3n. And the bottom is increasing by 6. So you can work with them, even though the answer is one fraction, you still work with them separately. So I have 3 times n, so if I put 1 in there, that gives me 3. Then what would I do to need to make it to get to 5? Well, then to make it go from 3 to 5, I would add 2. On the bottom, I put in 1, I get 6. What do I need to do to make it 7? I'd add 1. So the sequence, the pattern for this sequence would be 3n plus 2 divided by 6n plus 1. Then if we wanted to know what the limit of this sequence was, it would just be 3 over 6. So that sequence is approaching 1/2. It's never going to exactly hit 1/2, but it's going to get very, very close. Now this one's, the sequence here alternates in terms. Now the next term alternates in signs. So it goes positive, negative, positive, negative. So we're going to have either a -1 to either the n or n plus 1, determining whether or not it starts out with negative or positive. It could have started out as negative and then alternated. So right now, the first part of this is just to establish the order of the signs. Well, I want n plus 1 here because when I put 1 in here, I have 1 plus 1 squared. -1 squared will be +1. So that way, that'll guarantee the first term is positive. Then when you put 2 in there, -1 to the third is -1. So that guarantees that term's negative. So you just do it to make it match the first term, and then everything will run smoothly after that. Now the denominator, sometimes we have to be careful, because sometimes when they reduce to whole numbers like this, they won't always show you the denominator. But of course, 1 is the same thing as 1 over 1. So there's a 1 on bottom. So 1, 4, 9, 16 is basically 1 squared, 2 squared, 3 squared, 4 squared. So it would be n squared. The next one also alternates, but starts out with negative. So I would use -1 to the n, because when I put 1 in there, it's going to give me -1. That guarantees my first term is negative. And down the bottom, it has the same square pattern, but it's off by 1. In other words, the first term is 2 squared. The second term is 3 squared. So to make that fit, we just make it n plus 1 squared. That way, when you put 1 in there, you're going to have 1 plus 1 is 2, squared is 4 right there. So you just have to make it n plus 1 squared instead of n squared. Last thing I want to show you, which is not a big deal that I'm going to ask anything directly on a test, but its importance lies in sometimes in certain rules and definitions. It may tell you that a sequence needs to be monotonic or whatever for the following rule to apply. Of course, I would only use sequences where that was true. But let's take a quick look at what this is. A monotonic sequence is a sequence if the terms are non-increasing or non-decreasing. Non-decreasing means increasing with the possibility of adjacent terms being the same. It just means it doesn't go down. So it doesn't mean, but that's why it's not the exact same word as increase. Because I did that on purpose with this one. I went 1, 2, 4, 4. Well, it didn't increase from 4 to 4, but it didn't decrease either. So it was definitely non-decreasing. So 1, 2, 4, 4, 5, 7, 9. And you see these all have less than or equals to, meaning it has to be less than or equal to the next term. So that's monotonic. And the next one, they're going downward, getting smaller, 1/2, 1/4, 1/8. Here's a pair that's high, that's okay, 1/16, 1/16, nothing wrong with that. And then we have 1/32, and there we go. So, all right, that concludes this video on sequences.